thank you to Jesper and to all the organizers for inviting me, and it's a great pleasure for me to be here to celebrate Hubert's 60th birthday. As you heard from Jesper, that Hubert has a very broad spectrum of collaborators, and I'm from the other end of the spectrum. I work in condensed matter, and I had nothing to do with integrability until a few years ago in my postdoc, when I kind of stumbled upon it, and I showed up uninvited at Hubert's doorsteps and insisted that he listen to me. And so polite as he is, he invited me to come to Saclay and spend a few months, and that's where it kind of all began. And today I will tell you about some integrable models that could be realized with quantum electronic circuits. So you will see that there are physical systems experimentally realizable, which could be used to realize some of these integrable models. And so the paper that I read of Hubert and Paul was on the boundary sine-Gordon model, and it's a very simple and a paradigmatic model. I'm sure many of you know this much better than I do. So it's the model of a free boson on a half-line, and it has on the boundary it has a perturbation. It's a special perturbation that is an integrable perturbation. And I had read this paper of Paul and Hubert, where they had calculated the conductance in a fractional quantum Hall system. The idea is very simple in this fractional quantum Hall effect, that nu equals 1/3 filling. The edge modes are described by Lattinger liquids. You have to do some folding, and then you can get the boundary sine-Gordon model only at this filling. And so this is this famous curve. It's a bit unfortunate, the resolution is not ideal, but this jagged thing, this jagged thing is actually a solid line that's visible better, I think, on the screen. But so that's the curve that Hubert and Paul and others computed, and you can see the comparison with Monte Carlo and experimental data. It's very good, and it's one of these like phenomenal achievements of beta ansatz calculations. It's made to Jean-Marquis's book, where he says it's this tour de force calculation. That was something that I read during my PhD. And of course, then you can have boundary sine-Gordon model in other simple models like the spin chain. So this is an XXZ spin chain with the boundary field. This trivially realizes the boundary sine-Gordon model. It's not integrable lattice model that realizes it, but it's something that does it in the scaling limit. And now the question that I had was, each of these two systems, they realize the boundary sine-Gordon model, and they each have their own advantages and disadvantages. And my goal was to bring the advantages of both these systems together. And so, for instance, you see that the quantum Hall system is physically realizable. On the other hand, the spin chain is much more versatile. You can play around with it much more. It's numerically also more tractable. And so what the simple statement was that we could use a different set of a different physical system, that of quantum electronic circuits, which actually have these properties, and they kind of bring in together the best of both the worlds. Okay, so what are these circuits? So they are essentially very simple, and so the first element is something that you all know. It's a parallel plate capacitor. The Hamiltonian of this capacitor is Q²/2C, and so this is just the electrical energy in the capacitor plates. And the second element, it will play a very important role in our talk. It is this Josephson junction. So you can think of this as a parallel circuit of a capacitor and a nonlinear inductor. So the Hamiltonian now has two terms. The first is the electrical energy in the capacitor, and the second is the magnetic energy in the nonlinear inductor. So the form of this potential comes from the Josephson effect. Now what is very important is that the phi and the q, they are not classical C numbers anymore. They are quantum operators, and they obey commutation relations. There are also other elements like linear inductors and mutual inductors that could be used, but for the purposes of the talk, we'll just use these two very simple circuit elements. Now, the motivation for all this comes from experiments. So in the history of looking at dissipative quantum mechanics with this cosine potential theoretically, or the early experiments to realize such Josephson junctions is to the 90s. Now, in the recent years, there has been some revolution in the fabrication and investigation of these small Josephson junctions, which behave in a truly quantum mechanical manner. And so if you look at the progression of the field, you will see that the first experiments were done in the Devoré group at Yale, where they had about 43 Josephson junctions. And there was work done at Rutgers, where they had about 6 and 24 Josephson junctions. Then there was work done in Saclay here, right, in the condensed matter department, where they had about 100 Josephson junctions. And then more recently, in the group of Nicolas Roch in Grenoble, they have now an array of 1,500 Josephson junctions. And in Maryland, in the group of Manucharian, they now have 33,000 Josephson junctions. So this picture is actually taken from their paper. Each of these vertical bars is a Josephson junction. And there are 33,000 of them in the upper row. Then there is a short circuit, and then 33,000 in the lower row. And so some of you may know of these superconducting circuits. They are used to build also what are called digital quantum computers. There one builds qubits and then puts them together and then does operations on them to realize a quantum computing machine. Now here we are not talking about qubits. Each of these vertical bars is a Josephson junction, but there is no individual access to these junctions. So what we are looking at is an electromagnetic impedance environment where the modes of this electromagnetic environment are the plasmonic excitations of this array. And they can interact strongly because of the strong and dispersive Josephson coupling. That allows us to then probe strongly interacting many-body systems. To give you an idea of what has been realized in the experiments, I can show you the circuit of the Maryland group. And so, let me use that. And so this is the equivalent circuit. So you see there is a Josephson junction here and a capacitor here. And so this is the lattice Hamiltonian. So you will see that there is what is called the on-site repulsion term of the Bose-Hubbard model. This is the excess number of Cooper pairs, the Ni, on each island. Then there is nearest neighbor repulsion term coming from the capacitor of this Josephson junction. Then there is a chemical potential term. You can apply a gate voltage at each node. And there is Cooper pairs tunneling from one superconducting island to another. That's this cosine potential. What's very important is that n and phi are canonically conjugate. They have this commutation relation. And recently we computed the phase diagram of this model. And so if you look at the phase diagram as a function of the Josephson tunneling rate and the chemical potential, then you will see that the phase diagram has insulating phases. In between there is a charge density wave phase where the system has Snell-type order. But what's very interesting for us is that outside here we have a Lattinger liquid phase or a free compactified boson phase. And for those of you who are not familiar with the physics of the Bose-Hubbard model, we can remove some of the terms from this Hamiltonian that are kind of used to describe the circuit well. And so we can just look at these two terms of the Hamiltonian. This is just the quantum Hamiltonian of the two-dimensional classical XY model. So the circuit is realizing some kind of variation of the 2D classical XY model. So the Mott insulating phase is like the high temperature phase, and the superfluid or the superconducting phase is the low temperature phase of the XY model. That's what you can think of in this model.
Sorry,
yep.
Why is it 2D?
2D classical. 2D. Yeah. 2D classical. Quantum Hamiltonian or the 2D, yeah, maybe I should have written the word classical there as well. But good question. So, yeah. And so one of the quintessential properties of the Lattinger liquid is that it has algebraic decay of correlations. We can compute this, for instance, this correlation function that I'm showing you here. It decays with an exponent, which is the Lattinger parameter. And so here I'm showing you DMRG data that we got. And so here you can see on a log-log scale, it's quite linear, and the slope gives us the Lattinger parameter. And in principle, we know there's analytically also the Lattinger parameter all along the phase boundary. So all of this checks out. And this correlation function cannot be directly measured in an experiment. However, this exponent can be obtained by looking at transport characteristics across an impurity junction. And this is an idealized model, so in reality there is disorder in the system because you build the system on a substrate which has impurities, and so this leads to glassy phases here, but this Luttinger liquid phase survives. And it is this phase that has been observed in the Maryland group experiment, and in the Grenoble group they put together two such free bosons and coupled it with an impurity atom here. And so now it's a quantum electrodynamics problem, and they were able to measure the gigantic lamp shifts that occur in these kind of systems, which simply could not occur in nature because of the smallness of the fine structure constant. And what I want to tell you today is that with these circuits, we can actually realize much more than just free boson theories. And so my plan today is to show you that you can go from the free boson to some integrable models. And so the paradigmatic model here I'll consider is the sine-Gordon model. And then there is always a lot of resistance if you go to out and give a talk in a condensed matter seminar about stopping at integrable models. We need to look at generic models. And so we will see how to get to perturbed integrable models and a way to systematically introduce perturbations. And we will take the viewpoint of entanglement. So we will see that doing it this way also allows us at the same time with numerical or analytical techniques to compute entanglement properties of these models. And so the free boson. So the question is rather simple. How can we quantify entanglement of a block of size L of this one-dimensional circuit with the rest of the system? So one of the natural candidates is the von Neumann entropy, and we are looking at ground state 0 temperature, so it's all entanglement entropy. And what we know from previous works is that the entanglement entropy has a logarithmic scaling. So the coefficient gives us the central charge, and L is the subsystem size, and this is some non-universal constant. It's a very nice way of actually extracting central charge without knowing the plasmon velocity or the velocity of light in the system, because the other way would include computing ground state energies that necessarily requires the knowledge of the velocity. And now what we tried to answer was, how can we capture the long wavelength property of the system, that is the Luttinger parameter, through an entanglement measure? And what would also happen if you have what happened to the entanglement entropy in the presence of boundaries, and can we get the full spectrum of the theory from just an entanglement measure? And I'll show you that all of these questions can be answered both analytically and numerically because of a property of the system that is conformal invariance. So first, I need to show you how to impose boundaries in the system. And this is very important also for experimental situations where necessarily it will have boundaries. And so here, I'm imposing boundary conditions by applying two other Josephson junctions. And you can understand the boundary conditions as Dirichlet being realized by the junction energy to infinity and Neumann being realized by junction energy to 0. From an electrical engineering perspective, it's very trivial. So when the junction energy is infinite, it's a short circuit. Current flows through it, and phase is like the magnetic flux. Time derivative is 0, so short circuit, and everything is working. Now, spatial derivative of the current is just the spatial derivative of the flux is just the current. So if you delete the Josephson junction, there is an open circuit. No current flows, that's Neumann. Now, in the presence of boundaries, you have an additional boundary dependent contribution in the entanglement entropy, which depends on the Luttinger parameter. And we can actually compute this quantity analytically. And finally, I will show you that computing the spectrum of the entanglement Hamiltonian, so this is the reduced density matrix of this half of the system, and so the entanglement Hamiltonian is log of rho A, and the spectrum of this quantity gives us the complete spectrum of the conformal field theory. And this is very nice because here we are computing the ground state of the system with DMRG. That's something that still gives us the complete spectrum of the theory. It's not obvious, and it was something that was observed in an earlier theoretical work of Cardi and Tony. And so the calculations are very standard. I don't want to at all go into the details, but you just have to compute the partition function of the free boson on a cylinder with different boundary conditions. And we can do this, and then we can get exact expressions for the entanglement spectrum. So each entanglement energy level is labeled by two integers, k and l. And so you can compute exactly what the 0-point energy is. And you can then relate the k, this integer, which can be both negative and positive, to the dimension of the primary fields, and these to the descendant level. And you can also compute the degeneracies. This is all very standard. And then we can compute the change in the boundary entropy as you go from Neumann boundary condition to Dirichlet boundary condition here. And you can show this number is 1/2 log 2 over k. If you set k equals 1, you recover Affleck-Ludwig's boundary entropy for the Ising model. These are some numerical results for the circuit. So we computed the entanglement entropies for different bipartitioning of the system for Neumann and Dirichlet boundary condition. You see that as you apply the Dirichlet boundary condition, the entropy goes down. This is the G flow, if you want. And the amount by which it goes down is pretty much what we predict analytically. We can also compute the entanglement spectrum numerically, and this is what I'm showing you here. So this is the rescaled entanglement energies. And so this essentially gives us this integer L here. So it's non-negative integers, so you can see it's going up here. And this k is this k here. And so the predicted degeneracies for each of these are shown here. And you can see the diamonds are the DMRG data. So you see for each of the k's, the low-lying levels do show the predicted degeneracies. I wish the resolution was a bit better. I can promise you it really works for these low-lying levels. And then as you go higher up in this direction, then the pattern washes out because we are looking at a gapless system with numerics. And so there is a lot of truncation error. Now, having realized the free boson model, there is something rather straightforward that one can do, is to look at interfaces of the free boson model. This gets quite interesting. So here we can look at what we just computed again. So this is the bipartitioning of the free boson theory of the circuit. And we saw that the entanglement entropy had this logarithmic dependence. So if you look at the different bipartitioning of the system, you have this kind of dome-like curve. And you can also view this now as an interface between two different CFTs, but it's a bit trivial that the two CFTs are actually the same. Now, if you look at the cut at the middle and scale it with system size, you recover the central charge, which is 1. Now, how can we make it more interesting? So a very simple and physically realizable situation is when these set of Josephson junctions are different. What that changes is simply the compactification radius of the boson. So now if you look at the system, it has same central charges on both sides, but you have different compactification radii. And so again, in an electrical engineering language, we have two arrays which have different impedances. So it's the standard electromagnetic theory. If you have two impedances, there is reflection. So when you have reflection, then the correlation between this side and this side will diminish. And so that's why you will have an effective central charge now. This number is not predicted to be 1, but is lower than 1. And so we can see this in action a bit. So this is the data now for the entanglement entropy for different bipartitioning. So you see, as you go through the interface here, there is a jump. This is because the Lattinger parameters or the compactification radii on the two sides are different. Now we can look at the entropy at the interface and scale it with system size. And remarkably, it's still a straight line. And now the coefficient that we get is 0.975, and the predicted coefficient is 0.98. And so in this way, we can realize non-trivial interfaces between free boson theories, and currently we are working on realizing more interesting interfaces like topological interfaces. So this is what I wanted to say about the free boson theory. I want to now tell you how to include perturbations in the system, in particular integrable perturbations. So the model that we consider is the sine-Gordon model. It's a cosine perturbation of the free theory. And as you all know, there are solitons, anti-solitons, and breathers in the classical level. And when you quantize the theory, it still remains integrable. But in the single particle excitations, the spectrum changes. So on one hand, you have solitons, anti-solitons, and breathers. when this coupling beta square over 8 pi is less than 1/2. And this is the so-called repulsive regime when there are no breathers. And this is the Kostelis-Thouless point. In terms of circuits, it's very simple. So you start from the free boson theory. You choose parameters so that you are in the free boson phase. And then to realize the sine-Gordon model, the only change that you have to do is to replace this capacitor by a Josephson junction. So that's all I did. And now you can show that actually the model, the circuit realizes the sine-Gordon model with this relationship. So the sine-Gordon coupling is related to the Lattinger parameter of the free theory in this way. And so there is something that is an interesting feature of this circuit that I want to point out. So you see there are two Josephson junctions in each unit cell, and they do different things. So this junction tunes the beta, the coupling, the sine-Gordon coupling. And this junction gives rise to the sine-Gordon nonlinearity. It tunes the M0. And so with like this, you have two knobs that you can independently tune and probe the entire sine-Gordon regime. Now, I'll just show you some brief data of the quantum circuit lattice model that we got. Here, I'm looking at the expectation value of this vertex operator. And so Sergei and Sasha Zamrochikov, they had computed this expectation value, and they predicted the scaling. This follows from purely dimensional analysis. And so you see the dependence is algebraic. So if I plot on a log-log scale, it should be linear. And the slope should give us the beta square over 8 pi. And so here I'm showing the obtained data. This is what is shown here. And this is what you expect. And so you see the agreement is quite good, which gives us some confidence in our calculations.
So there's a
Yeah.
normalization factor in there. How do you get rid of that?
I'm just plotting the log-log dependence. So the normalization is additive.
Oh, okay. So
Yeah.
Okay. Sorry.
Yeah.
So it's just check. So you don't need all this very elegant stuff of Sergei.
No. This is just that's why I said it's just dimensional analysis. Yeah. But the normalization is important, as Paul rightly points out. And so this is important for the two-point correlation function. This is now what I'm plotting. This is the two-point correlation function of the vertex operator as a function of the distance. And it is for parameters. As you see, this is quite deep in the attractive regime, but there are many, many breathers. And here I computed the normalization from computing the one-point function, used it here, computed also the plasmon velocity. Everything was computed, and this is what we get. There is no fit. It's just plotted on top of each other. And so you see the agreement is again quite good, which gives us confidence. And since this work, I had computed also the repulsive regime, and that's something that's also accessible. The Kostelis-Thouless point turned out to be more difficult, but overall, I think we have a fair amount of confidence to realize at least a wide range of the sine-Gordon couplings.
Remind me how many form factors there are?
I mean, yeah, we went to 2 particles. Yeah. And we were able to also compute the entanglement spectrum, and so this is the entanglement spectrum. And you can see, if you look closely, you will see some pattern emerging, and the predicted degeneracies can be obtained again from the partition function of the free boson for Neumann and Dirichlet boundary conditions. And if you look closely, you will see that indeed the pattern is, for the low-lying levels, it's exactly what is predicted. And then it starts to get worse or somewhere around here. And that has 2 sources of discrepancies. Firstly, that there is some finite truncation, the numerical effect, but there is a more unavoidable discrepancy source, which is the non-integrable nature of the lattice model. This, for instance, would not be true for the XYZ spin chain regularization, where the model will have perfect degeneracies, exactly these degeneracies throughout the spectrum. So in this way, I hope you can start to appreciate that we are just computing quantum circuits for these well-known spin chains. So this is the spin chain for the free boson. This is the spin chain for the free boson. That's the XXZ chain. And this circuit is just for the XYZ chain. And now what we want to do is to try to understand how we can realize perturbed models. And so we look at a very specific perturbation of the sine-Gordon model. That's this perturbation. It's cosine 2 beta phi plus delta. And recently there have been some renewed interest in this model. There's some Ising phase transition that occurs. And my goal here is to just show you how the circuit can be realized for this double sine-Gordon or perturbed sine-Gordon model. So we start from the sine-Gordon circuit. So this is the picture that you already saw, and this realizes these two terms of the Hamiltonian. Now I want to realize this term. And the way it works is that I just need an additional circuit element, which is what is called a 4E Josephson junction. So a Josephson junction allows Cooper pairs to tunnel. So that's charge transport of 2E. Now this is a special kind of Josephson junction that allows pairs of Cooper pairs to tunnel, not Cooper pairs. Sorry. Now it might seem strange. What is this weird Josephson junction? It turns out that quantum computing folks have already thought about this. This is the so-called 0 pi qubit. So if you put 4 normal Josephson junctions in a ring and thread it with a magnetic flux, you realize this 0 pi qubit, which allows tunneling of pairs of Cooper pairs. And not only has it been theoretically proposed, it has been also experimentally realized in the Rutgers group, where they have built precisely these rings that you see above, about 20 of them. But this circuit is still to be built or analyzed, and we plan to do this in the coming years. And as you can see, what we are trying to do is a bit like Fourier cosine transform. So these are the first two harmonics. We can potentially add more terms in here, and that would add more terms to the in parallel here. Okay, so that's what I wanted to show you. I will just now show you some model that we are looking at now, which can be viewed as some extensions of some of the works that we have done. So our goal has been to realize models which go beyond the free boson theory, and so this was the boundary sine-Gordon model that I showed you to start with, and this is the quantum circuit for it. And now what we want to do is a very special C=2 theory, and this is the so-called boundary double sine-Gordon model. And so here we have now 2 free bosons on the half line. They don't talk to each other in the bulk, but on the boundary they have this very special interaction. It's cos times cos. And you will note that beta 1 and beta 2 are 2 different coupling constants. They do not have to be equal. And the interest in this comes from Hubert's earlier works, these works here, where he had conjectured a fixed point for that seems to be there only for beta 1 square plus beta 2 square equals 4 pi. And my goal has been to either prove or disprove his conjecture. And just one word of caution is that you should not think that this is the only fixed point. For C=2, there is a zoo of very complicated things. So this work with Ian and Hubert and Masaki Yoshikawa, they had looked at a lot of these non-trivial fixed points, and there are other fixed points which are more like the interfaces I described in the works of Bachas and others. So we will focus on this specific fixed point and try to see how we can realize it with a quantum circuit. And so the prediction that Hubert had worked out in these years was that there is this one specific manifold, which is when the squares of the couplings come up to 4 pi, and on this specific manifold, the ratio of the G functions in the UV and the IR are different. So this is the so-called trivial fixed point, when the squares of the coupling do not sum up to 4 pi. Then you see you have this ratio of the G functions. On the other hand, if you have the squares of the coupling summing up to 4 pi, then you have this ratio of the G functions. The formulas are quite different, and if you just plot them as a function of beta 1 square over 4 pi and beta 2 square over 4 pi, you see that they have different, from entropic contributions, different parameter spaces have different stable fixed points. And the statement is that there is this integrable manifold, which is only this line here. on which this fixed point arises. This is quite remarkable, and I want you to appreciate it because from purely entropic contributions, this is favorable in the entirety of this phase. And so this is something that we are trying to see, how we can actually see this evidence of the fixed point only on this line. And so we have done some numerical calculations. I will not go into them in detail because in the interest of time, but let me just show you the circuit that realizes it. And I've given you the boundary sine-Gordon model on the left-hand side for comparison. So you see now we have two free bosons on a half line, so that's just these two Josephson junction arrays. So this array and this array realizes phi 1 and phi 2. You will see that the junctions here and here are different. That realizes that beta 1 and beta 2 are different. And now the question is, how does one realize this cos-cos interaction? Turns out it's very simple. Instead of having one Josephson junction in the boundary sine-Gordon model, you need two Josephson junctions in the boundary double sine-Gordon model. And this precisely gives rise to this Hamiltonian here. Okay, so that's it. I want to thank my collaborators. The numerical part of the work was done with Johannes Hauschild at Berkeley and Frank Pohlmann in Munich. And on the theory, on the analytical side, I was working with Hubert and Dirk Schuret. Thank you, and happy birthday, Hubert.
Thank you, Ananda. Are there any questions?
So maybe just a naive question: is there some way to do this in 2 dimensions, or is just limited to one-dimensional quantum field theory? Or can you do if you do a 2D circuit? Will it have some interesting behavior, or is it not expected?
No. Sure, it will have interesting behavior. It will just be more difficult. So I had a slide here that I don't see because it's. Yeah, but let me just say it in words. So you saw that the array was one-dimensional, and you could probe the array from the side, right? And so you can still stay in the plane of the system. However, if you make a two-dimensional array, then you have to necessarily go at it from the third dimension. That makes the experiments much more difficult. But 2D arrays such as these have been built. For instance, Andrew Hauck at Princeton has actually built a two-dimensional array of about 70 Josephson junctions.
Thanks.
Sorry, but in 2D, the sine-Gordon, what is the meaning? I mean,
yeah, no, they didn't build the sine-Gordon. They just built a 2D array of resonators and Josephson junctions, but
so
not the sine-Gordon.
You mean other field theory, not?
Yeah. They were looking at quantum codes.
Okay.
They were looking at a topological code. So, yeah.
Okay. So if there are no further questions, let's.
I think.
There's one more question. Excuse me.
Can you disorder your system by changing the capacitance, or?
Yeah. So you can disorder indeed. Actually, the ordered thing is more difficult. So, for instance, here, if you don't work for it, these junctions here would be different, and that would give rise to an inhomogeneous Lattinger liquid, for instance. With varying couplings. You can also change the capacitors. That would change the kinetic term of the free boson. Yeah, you can. This is like where we are begging the experimentalist to be careful and keep the junctions homogeneous. But by default, it would be inhomogeneous. I don't know. So, for instance, something that would be very interesting is the fate of the sine-Gordon model in the presence of disorder. Do these solitonic states localize? Do you have states below the gap? That would be interesting. I don't think it has been analyzed. So, yeah, good question. So here, this is the chemical potential where naturally you have disorder. You don't even have to put disorder. You can just make the array big enough that you will at some point start hitting these disorders. And then imagine that you have the sine-Gordon model in the presence of this chemical potential disorder, and then ask the question, what happens to the states of the sine-Gordon model in the presence of disorder? That's a very good question. So.
Okay, I propose we thank Ananda again and